Hello everyone, my name is David Chan, and in this video, I will be talking about the paper titled Recoverable Mutual Exclusion with Constant Amortized RMR Complexity from Standard Primitives. This paper is authored by me and Philipp Woelfel from the University of Calgary. Let us start with a short outline. First, I will explain what the recoverable mutual exclusion problem is. Then, I will briefly describe the related work on the recoverable mutual exclusion problem. Next, I will give a short overview of our algorithm and our proof. Finally, I will conclude with some problems that remain open. So let's take a look at the recoverable mutual exclusion problem. Yes. In this problem, there is a set of processes that begin in what is called the remainder section. So in this video, I have chosen to draw these processes as little smiley faces. At any time, any process inside the remainder section can choose to leave in order to enter another section that we call the critical section, as shown by this rectangle. After it has finished what it wants to do within the critical section, the process can then exit and return to the remainder section. Now, what makes this different from the normal mutual exclusion problem is that processes can clash, and when they do, they are expected to eventually revive, at which point they will have to find a way to rejoin the cycle. Now, a solution for the recoverable mutual exclusion problem must specify code to execute by each process for each of these three arrows. We call these three arrows the enter, the exit, and the recover protocols. The resulting executions from this mutual exclusion algorithm must satisfy a few properties. Let me just fast forward the video. At the minimum, there must be three properties that are satisfied, and these are mutual exclusion, deadlock freedom, and critical section reentry. Let us take a look at what each of these properties mean. First, regarding mutual exclusion, we look at the critical section. If in some execution, there is a time when there are two or more processes in the critical section, then we say that mutual exclusion is violated. For deadlock freedom, we look at each of the three arrows. If in some execution, there are processes that completely block each other from completing the code in the arrow, effectively clogging up, then we say that deadlock freedom is violated. Finally, regarding critical section reentry, we look at the critical section again. If some process clashes within the critical section, the critical section must then be reserved for this process. No other process may enter until this process re-enters the critical section. In addition to these three fundamental properties are many stronger but optional properties. For example, first come, first served, starvation freedom, and wait-free critical section reentry. But these properties are not the focus of the paper, and so I will not discuss them within this video. So let's talk about the solutions for the recoverable mutual exclusion problem. These solutions are typically measured by their RMR complexity. Intuitively, this is the number of meaningful shared memory operations a process can be forced to take in a cycle through the critical section or from a clash. There are two distinct models for measuring the RMR complexity of an algorithm. In the first model, which we call the cache coherent model, processes keep cache copies of the registers they have read. If they later read the registers again and find that the values have not changed, those reads would simply return the values inside the cache, and so these reads do not count as remote memory access, as RMRs. Thus, the number of RMRs is simply the number of operations minus the number of repeated reads. In the second model, called the distributed shared memory model, the processes have ownership over disjoint sets of registers in the system. Intuitively, if a process owns a register, that register is local for it, is quickly and easily accessible. And so when a process performs an operation on a register it owns, it doesn't count as an RMR. Thus, the total number of RMRs in this distributed shared memory model is simply the number of operations performed on registers that are not owned by the process. In this video, we shall be focusing primarily on the first model, the cache coherent model. Now, let us discuss some solutions for the recoverable mutual exclusion that have come up in related work. Golab and Ramalaju presented the first recoverable mutual exclusion algorithm. It uses the standard primitives compare and swap and fetch and store, and has O log n RMR complexity in the CC model. Golab and Handler then improved on this result, achieving an RMR complexity of O log n over log n. Next, Jayanti, and Joshi then showed that this RMR complexity can also be achieved in the DSM model. Now, a few solutions have managed to go under the log n over log n bound, but only with certain caveats. In this conference, Doket and Mitter presented an adaptive solution for the RME problem. If there have only been F recent clashes, then the RMR complexity is reduced to O1 plus the square root of F. Thus, their solution is significantly more efficient than the log n over log n bound when the frequency of clashes is low. Golab and Handler also give a solution with constant worst case RMR complexity, but this solution requires the non-standard primitives fetch and store, and double word cast. These primitives are not supported by current hardware architectures. Next, Jayanti, and Joshi then showed that if we do not allow double word compare and swap, but still allow fetch and store, we can achieve an O of F RMR complexity in the CC model, but an O1 RMR complexity in the DSM model. In this paper, we take a very different approach. Specifically, we use the fetch and increment standard primitive instead of the more typically used fetch and store. In doing so, we achieve O1 amortized RMR complexity in both the CC and the DSM models. So without further ado, let us discuss our algorithm, or rather, a very simplified version of it. At the core of our algorithm is an infinite array of class objects that are labeled A1 to infinity. Intuitively, processes that want to enter the critical section will queue up using this array A by placing their process IDs in the slots of the array and entering the critical section in the order given by A1 to infinity. However, trying to place a process ID into each slot sequentially is very inefficient. So we also have a fetch and increment C, as shown by this green square. And when processes want to enter the critical section, they would first take a unique ticket number from C via a fetch and increment operation, and then join the array at the specified index. Finally, we have another compare and swap object that we call token. And this token object is simply used to indicate our current position inside the queue A. So, at a high level, when a process P leaves the remainder section to try to enter the critical section, these are the steps that it takes. First, it takes a ticket from the fetch and increment C. So let us say that this ticket it takes from C has the value I. Then in the next step, P would look for the I of slot of A, and it would put its process ID into that slot. Next, P would try to move the token forward through the queue. This would hopefully allow more processes to enter the critical section and continue moving the queue forward. Finally, P waits for permission to enter the critical section, which will be given once the token moves to A of I. Now, when exiting the critical section, P would only try to move the token forward, which works exactly the same way it does in the enter protocol. And then it would just return to the remainder section immediately. Now, I am leaving out a lot of details here, but this is essentially correct when there are no clashes. But in the case when there are clashes, there is a problem. Consider the what if worst case where a process that takes a ticket from C via a fetch and increment operation immediately clashes. So this process, let's say the ticket had value I. This process took the I of ticket from C, and then he clashed and lost it forever. Now, this process was supposed to occupy the I of slot of A, but no longer remembers which slot he should have been to. And nobody else knows what slot he should be in. So he has no way to know that he should occupy AI. Thus, we could end up with a situation where there is a gap in A that will remain forever empty, even after this process P recovers from its clash. Then, when processes that try to move the token reach this gap, they could end up stuck forever because they wouldn't know how to deal with this gap. Now, in this paper, we solved the issue by allowing skipping over gaps under certain conditions. First, we add another fetch and increment we call D, and this fetch and increment is incremented whenever a process recovers from a clash or joins A. So intuitively, the value in D would be a lower bound on the number of tickets that have been used or lost. Now, consider the processes that are moving the token. When these processes find a gap, they will skip this gap only under the condition that C is no more than D. In such a circumstance, it is entirely possible that this gap will never be filled because the ticket has been lost. We now give a short overview of the proof. First, to see why the algorithm has constant amortized complexity, refer to the skipping mechanism. We see that the main reason there are extra RMRs incurred is precisely because gaps may be skipped. And such gaps may not be the result of clash processes, but rather slow processes. And when these slow processes find out that they have been skipped, they will be forced to effectively redo their entire enter protocol from the beginning. Now, these RMRs in code are very inefficient, but we have an upper bound on the number of skips because skips are only done when C is less than or equal to D, and D is only incremented when the process recovers from a crash or joins A if after it gets a ticket from C. So we see that the number of skips is effectively bounded by the number of crashes. Thus, all of the extra RMRs incurred by skips can be charged to the crashes in a manner that achieves constant amortized RMR complexity. Next, mutual exclusion is achieved by the use of the compare swap token. This is because only the process that's currently selected by token is allowed to enter the critical section. Next, deadlock freedom is achieved by the infinite array A, which makes the processes in the enter protocol queue up and enter the critical section in order without any deadlocks. Finally, the critical section reentry property is satisfied by ensuring that the token is not movable when there is a process inside the critical section. And in fact, if this process that's in the critical section is crashes while it's still in it, even then the token is not allowed to move. In conclusion, we have constructed a recoverable mutual exclusion algorithm with the following properties. It has constant amortized RMR complexity, and it uses only the standard primitives compare and swap and fetch and increment. However, this algorithm requires unbounded space, and in the paper we show that it only satisfies a weak version of the highly desirable starvation freedom property. Naturally, these leave some open questions. For example, is there an improvement that uses bounded space and satisfies strong starvation freedom? We strongly believe that this is indeed the case. But the most interesting question is there an RME algorithm with constant worst case RMR complexity using only standard primitives? This question remains open. And that concludes this video. Thanks for watching.